well from your evening. You're going to have an exciting talk now from Moni, who's going to talk on the privacy of the analyst and the power of the state. So, over to you, Moni.
Thank you. I suppose you say privacy, I say privacy. So this is joint work with Cynthia Dwork and Salil Vadan. So here, for those of you who want to go back to sleep, this is a one-slide version of the talk. Well, what do we mean by privacy? So privacy, of course, is a very loaded term, lots and lots of different meanings. We'll talk about differential privacy. I assume that many of you know, but I'll explain what it is and what it is good for. Privacy of the analyst. So the issue that we're interested in is how to maintain the privacy of the queries, also the data, not only the data. The data is what the usual concern of differential privacy. We'll be interested in maintaining the privacy of the queries to the data. In the power of the state, of course, the power of the state could mean various things, but in this case, the issue we are concerned with is that you have privacy of the queries arise only if there is a coordination of noise, only if the answer to one query depends on the other queries asked so far. And actually what we show is that this is necessary. You have to maintain state between queries, and therefore the issue of giving privacy to the analyst is a non-trivial one. So this was the one-slide version, and now let's see some more detail. So we have lots of data. Even since the modern age, since the 19th century, governments had lots of data, but nowadays lots of companies have huge amounts of data. And here in Britain, of course, there is also public surveillance information in the form of CCTV, and all over the place there is the issue of RFIDs. We can, of course, devote a whole conference to the topic of privacy in social networks. And the point is that data contains personal and confidential information. And we would like to derive some social benefit from analyzing large collections of data. And here is an example of such, not huge amount, but a small amount. Does anyone recognize the map? Exactly, yeah. So this is the map that Dr. John Snow, who figured out that cholera has to do something with the water source, drew up after the London epidemic of 1854 in order to convince people that there is a connection between the cholera cases and the Broad Street pump. So this is a wonderful example, also a little local, that of what you get from when you analyze large collections of data. But the point is we want to do it in a privacy-preserving manner. And if we're not careful, almost any data usage that is not crafted in order to protect the privacy will leak something about individuals. And we want to be able to talk about it in a rigorous manner. So the Holy Grail, so to speak, is to get the utility of statistical analysis while protecting the privacy of every individual participant. And of course, ideally, privacy-preserving the sanitization will do should allow reasonably accurate answers to meaningful information, to all information. So one issue is, can we phrase it in a meaningful and achievable manner? So there are positive and negative results in this area, and this is not what I'm going to talk about. So first, the setup that we're talking in is we have a database, which we just mean collection of data. We have someone that we call the curator or the sanitizer who is in charge of cleaning the data. And that person, well, there will be two possibilities. This person publishes a clean version of the data, which presumably does not violate their privacy. This is one option. The other option is the interactive case, which would be more of our concern, where queries come to the curator decides how to, consults the data and decides how to answer them. Another query comes, the curator consults the data and perhaps the other things he was asked about and answers, and so on. So, the problem, just to say, the problem is difficult even if the curator is completely trusted, and basically we will think in this talk is the curator being trusted. Of course, we can ask this as well, and the data itself, they are involved. That's not the issue. The issue is you learn something from the queries. So unlike secure function evaluation, where you want to be as good as the ideal solution, here the question is, what can you do in the ideal case when everyone acts as an angel? Okay, so perhaps you may think that this is not exactly in crypto, but actually I disagree. There are tight connections to cryptography, and I hope I will convince you by the end of the talk. I could have given you actual results. I could have described results that are actually show tight connections. I wouldn't show any tight connection. For instance, you can show connections between the tracing trader problem and some of the issues I'll talk about. But I'm not going to go along this route. I'll show you more subtle connections to cryptography. Okay. So we're interested in databases that teach us something. For instance, the database teaches us that smoking causes cancer. So you could say, but this is against some smokers' interest because his insurance premiums will rise. But this is true even if that smoker is not in the database. Okay, so our goal is to study that smoking causes cancer, and we haven't really, by figuring that out, we haven't really violated the smoker. We haven't really violated that smoker's privacy, because this is our goal, and we would learn it whether this S is in the database or not. Okay, and hopefully the good story ends when the smoker enrolls in a smoking cessation program, and then there isn't any issue at all. So this is what differential privacy is about. It wants to limit the harm to the teaching, not to the participation. So the outcome of any analysis is essentially equally likely, independent of whether an individual joins the database or refrains from joining the data set. Okay, so here we have two databases. The two databases are neighboring, so the only difference between them is one individual. We'll either talk about when you switch an individual, or when one has an individual and the other doesn't. And what we want is that these two outcomes, where the curator publishes, in this case in the non-interactive case, but we can also talk about the interactive case, the output of the curator should be very similar. And the output of the curator, when you'll see the definition, of course, it has to be a probability distribution. It cannot be just you cannot have a deterministic curator. And what we would want is that these two distributions would be very close to each other. So we say that a sanitizer M gives epsilon differential privacy if for all adjacent databases D1 and D2, and all possible outputs sets in the output in the range of n, for every the ratio between the probabilities of getting that output in database D1 and the ratio of getting it in D2, this is bounded by e to the epsilon. So if you look at all possible outputs, you look at the ratio, and this is going to be bounded.
Exactly. This means that the difference between D1 and D2, that somebody is not in the database, would be added. What exactly does that mean?
Their data is not in the database.
So data is always associated with Prof, because I could be
Yes, right. No, you
together with
right.
Greg, and maybe it's considered his record or something like that.
Right, you're right. That's an issue. You're right. This is the shortcoming of differential privacy. You look at the database as a collection of n records, and you're concerned with the privacy of a particular record. You're right, it doesn't cover everything. And in fact, there is an impossibility result that you cannot have something like semantic security here for this. Even this epsilon is not negligible. So we definitely depart from crypto here, that we're talking about non-negligible events. But you cannot really have the equivalent of semantic security in this area. So therefore, we're restricting ourselves to looking at. We view that the adversary is knowing everything but a single record, and yet he cannot tell whether this record is in the database or not in the database. That's the point, and that is even given the output. So it's true for all outputs. This is the requirement here, unlike most requirements in crypto. Here we want given that after the fact you cannot tell. So the whole point is that participation in the data set poses no additional risk. So when you are asked these forms to fill out, can we use your data, you shouldn't be concerned by more than e to the epsilon. Yeah.
So, here is it just the randomness of
the mechanism,
okay, so
of the curator, yeah, of the sanitizer curator mechanism.
nothing else in the data or anything is considered?
No, you could of course start making such models, but we're not. We're in the from the data set point of view, we're in the worst case. Yeah.
Are your databases consisting of a single table, or they are databases in many tables?
No, a single table with n records, certainly in this talk. We'll also be concerned with very simple queries, as you will see. Okay, so here is an easy way of getting, let's say you have a counting query. You have names and the tag 0 or 1, and we'll have one query. What is the number of participants with tag 1? So the natural idea is to output the number of the real answer plus noise. And the noise is drawn from a Laplace distribution with parameter 1 over epsilon. And the property that we have is that sort of the probability of noise k minus 1 versus noise k behaves exactly as we would like it to have. So you cannot tell whether a participant, where you perhaps know their tag, you know everyone's tags, you know about a potential participant, and you still wouldn't be able, if you use this sort of noise, you wouldn't be able to tell whether that participant is in the database or not. So this is an example of the differential privacy. Here is an example of something that is not differentially private. You sample from the database, and you publish everything about that sample. Or even if you answer just according to the sample, even that on its own would not be differentially private. If you just sample from the database and give, of course, the weighted version, the reason it would not be differentially private in such a way, because if everyone has 1 and there is a single 0, and the answer is not all ones, you know that 0 is in the data set. So even though the probability of sampling him is that person is some fraction of n, if it happens, you know that it happened. So that's not differentially private. And we'll talk about a relaxation of differential privacy, epsilon delta differential privacy, where we are relying ourselves and added, the ratio is bounded, we're allowing ourselves some added place where things go wrong. And this delta we would want to be negligible. So epsilon can be anything, but think of it as like a small constant, or maybe a tiny constant, but definitely not negligible. It cannot be negligible if you want to get meaningful answers by a hybrid argument. But delta, think of it as negligible. The delta is when things go wrong, like you draw from a distribution and it's way out there or something like that. Okay, so in general, differential privacy has been hugely successful. You have algorithms in many settings for many tasks, and it has several important properties. Composability. So you can say something, if you apply the sanitization several times, you get a graceful degradation. And we'll say something about that. You have robustness to site information in the sense that I'm told you exactly what the adversary knows, knows everything except the missing record. Okay, so we don't have to worry, like in the story about the IMDb, about the Netflix challenge where the people were able to use it to break privacy, Shmatikov and Narayanan, because they were able to take inside information, the IMDb. So suddenly that came out of left field, this database, this IMDb database. The designers did not think of it. But here we are telling you exactly, they know everything except one, whether a record is in or out. So we'll be concerned with counting queries. You can thinking of more complex ones. So we're thinking of we have a universe U. We have n individuals, each contributing a single point to the database. So we'll call the database X of size n. The query is another subset. And the question is, how large is the intersection? What fraction out of between 0 and 1 is the size of the intersection? This is going to be the query. It's a very simple one, and we'll be aiming for a relaxed accuracy, something with additive error alpha. Okay, and this is not so bad because if we're talking about statistical analysis, of course, there is some inherent noise anyway. And in fact, you can show that you cannot answer a whole lot of queries if the noise is, let's say, less than square root of n. If the accuracy is less than square root of n. So here, what can we do? Well, one thing is we can use the Laplace mechanism. And if we apply it t times, oops, this k should be t, right here, the privacy loss. So you can, the straightforward answer is that you lose t times what you lose by applying it once, but in fact, you get something, if you go with epsilon delta differential privacy, you get something closer to square root of t times what you would lose. So if you apply t times, you lose square root of t times. And this was shown by Dwor, Rothblum, and Vadan. So if we do it, well, if we want delta equals 0, we can apply it less than n times. If we are aiming for epsilon delta differential privacy, then it works at most n squared times. But what happens if we want many more than n squared queries? We want to be able to answer lots and lots of queries. So here, Blum, Liggett, and Roth in 2008, they said if you actually don't answer each query independently, give some coordinated noise, and do it, give careful coordination. And if you do that, you'll be able to answer hugely many queries, okay? And after some improvements and after making the algorithms constructive, the final answer is that you can answer any number of queries, let's say of the type that we saw. The dependency on Q is something like logarithmic, plus some other terms. And the error, the dependence on the error is log Q times square root of n. And the algorithm we'll be using is the private multiplicative weights algorithm of Hart and Rothblum. And it allows, it answers the queries as they come. So you don't know all the queries when you start answering. But you, when a query comes, you give an answer, and you can answer any number. And all you know is that the error is going to deteriorate with logarithmically with the number of queries that you have answered, and it's going to be square root of n, where n is the database size. Here, of course, it's 1 over square root of n if it's between 0 and 1. I think I'm going to alternate a few times between renormalizing and not. I hope it wouldn't be too confusing. Okay, so let's see this algorithm. So it's based on the multiplicative weights algorithm, which is a very powerful tool in algorithms design, where the idea in the multiplicative weights algorithm, the non-private version, is that you learn probability distributions iteratively, and in each round, or it doesn't have to be a probability distribution, but you treat it as if it's a probability distribution. And in each round, either the current distribution is good, or you get lots of information on the distribution and you can update it, and that cannot happen too often, because if there's a limited amount of entropy to begin with, and if each time you get more information, you cannot, I mean, it's going to be bounded. So the number of updates is bounded. That's the point of the multiplicative weights algorithm. So here's the private version. We are going to maintain a distribution D of the universe. We're going to start with the uniform distribution on the database. And we're going to repeat up to k times. So k is going to be, we're going to say this is not going to happen more than k times. K is the number of updates. So we'll have some threshold t, a fixed threshold. And then each time we're going to make it a noisy threshold by adding to it some Laplace noise. And the way the algorithm goes, you receive a query, you look at the answer. This is like the simple Laplace mechanism, right? You add noise to it. This is a potential. This is could be an answer, except if we output it too frequently, we are going to violate the privacy. That we know. That you can see that Laplace, just giving the Laplace answer each time is too dangerous. But instead, our candidate of answering would be D itself, the distribution itself. So you look if the difference is not too large. If the difference between the answer in the current database and the potential Laplace mechanism, the difference between these two mechanisms is bounded by this noisy threshold. If it's small, then you output whatever the current distribution tells you. If it's large, you have an update step. And you output, so you output the answer of the Laplace mechanism, and then you update your distribution, giving more weights depending on the answer and whether it was in the correct direction. You give to the points that were deprived, you give more weights. Those that were overweight, you reduce their weight, and you make sure that it looks like a distribution.
So Moni, do you maintain the database or distribution?
The distribution.
So QOD is like you sample a database according to the distribution?
No, it's, well, it's just what the expected answer is on the distribution. Yeah. Now, D is not secret at all. If you follow the algorithm, you'll know what D is. If you follow the outputs of the algorithm, you'll know what D is. It's not secret at all. Okay, so the algorithm fails if more than k updates, and the goal is to show that this doesn't happen frequently or happens only with low probability. This should be absorbed by the delta, or not even by the delta. You can even make delta 0. This is not what makes it. This is the state. So this distribution is a state. We're talking about algorithms that the curator maintains a state. The state depends on the previous queries. And as I said, it can be completely public. You can figure out what it is. I mean, you may as well, the curator may as well publish it, at least for the proof. You can think of it as public, because you can figure it out. If there is an update, you reweight the distribution completely deterministic. And the only issue is if you see whether it was if there was an update or not, and let's say that's not a big secret, maybe because things look a little different if there was an update or not.
So, Moni, x of q is the query.
It's the real answer. This is the real answer. This is the real answer, and you add noise to it, and you compare it to what the current distribution tells you. And if it's large, if it's too large, you update, and if not, you answer according to the current distribution.
So what is Q of I in the last line?
Oh, whether I is in the Q query or not. This is how you update each point. If it's under or over. Anyway, so the way the algorithm is analyzed is showing that the number of times an update can happen is just not too large. As long as the Laplace noise is never out there, you can show if that never happens, and Laplace has pretty good concentration. So as long as that doesn't happen, the number of updates just cannot be large, simply using an argument, an entropy type argument, that the entropy goes down or the relative entropy goes down by a certain amount in each update, and so it cannot happen too frequently, and then you can show that telling you where the updates happen isn't too bad, and then you can show, let's say, give each round is completely private because, well, you're using D itself, and then you can use some sort of composition because you don't have too many update steps, so you can use the composition. So this is how the privacy would work. And what you get is you get for any number, for any beta, delta, and epsilon, you can get in T, you can get something that is epsilon delta differential privacy. In alpha beta accurate, where alpha beta accurate means that the answer is accurate to within alpha, except with probability beta. So you have some log dependencies on the size of the universe, on delta, beta, and T, the number of queries. And other than that, it's square root of n. Okay. The point is about this algorithm is that the distribution is privacy preserving for the individuals, but not for the queries. If you know the distribution, you know what other queries were asked. You can see that because you'll see whether it has higher weight and whether it has lower weight. It will have higher weights if the queries were concentrated in a certain region. So the state itself does not preserve the privacy of the queries. And this is our concern. So the question is coordination necessary? And there are two reasons to ask. One, as I said, is because the state may leak information about other queries. The other is if you want to run it in a distributed manner, you have lots and lots of different servers who will be answering these queries. And the question is, should they coordinate their answers? Or can they just work on their own? For instance, in the Laplace mechanism, they can do whatever they want. They don't have to follow they don't have to do anything central. So why do we want to keep the queries secret? Well, very much like as in, for instance, PIR, private information retrieval. The questions you ask, of course, may be embarrassing, maybe even persecution, leakage to competitors. If there are all the stories about the patent that, why do you want to set up a patent database to see what patents are being searched, etc. If you're in law enforcement and you're querying a database, you don't want the criminals to be alerted that you're after them. So there are lots of reasons to have the privacy of the analyst. And for instance, yeah.
For all of those concerns, doesn't it make more sense to use a cryptographic solution, like a 2PC or something like that?
Like
a 2PC, a secure evaluation to protect the privacy?
No, it wouldn't. Okay, from the curator, you're talking about the curator?
No, I'm saying.
No, but it's not. You know from the answers. From the answers, I'm asking the mechanism some questions. I'm getting answers, and from that, I'm deducing something about your questions.
No, right.
So this is something that secure functional evaluation does not resolve.
So you're envisioning a situation where the analysts ask questions, but the answers are published in some sense.
No. I mean, could be. I mean, this is you could think of such cases as well.
So then I don't understand. If it's only between the analyst and the curator, then they can just do a secure.
No, but there are two analysts.
Oh, sorry.
Okay, sorry for not being clear. There are we'll have many analysts. Our results are best when there are where there are only two of them, or a small number. But there are two analysts. I'm asking questions. You're asking questions and getting answers. I'm asking questions and getting answers. And
I want to see if there can be an economy of scale between the analyst questions and the accuracy you get.
No. From the answers, look at the state. Let's look at this algorithm.
No, I'm just saying.
You asked a lot about things in Cambridge. Lots of queries about things in Cambridge. And then I come along and I want to know whether I'm suspicious that you are actually Cambridge. So I just want to see whether the database is now biased, the distribution is biased towards Cambridge things.
Right, but an easy way to protect that would just be using independent Laplacian noise, right? So it means
No,
0%.
no, but that allows answering a limited number of
Right, because of the accuracy. That's what I meant. Yes.
Yeah.
So you want to.
So we have a number of well, we'll see what we have, but we have a number of independent mechanisms, and we'll actually show that there are both. These are the limits. These are the best possible. Okay. So we want privacy for the analyst, and what we can show is that in fact you cannot answer if you have a stateless mechanism as the Laplace one. You cannot answer more than n squared counting queries, and this is tight, and so this shows that there is actually, because before we had only logarithmic dependency on the number of queries in terms of the accuracy. So this is, so what we have is that if you want to give any non-trivial type of accuracy, you cannot answer more than n squared queries. Whereas before we saw that the dependency of the number of queries has to be only logarithmic, so there is an exponential bound here.
So this is more generalized than the Dinur-Nissim, right? So they assume something more specific. It's the
No,
same.
Dinur-Nissim says, for instance, that you cannot answer too accurately or too many queries. They show, yeah. No, this is right. Dinur-Nissim is a bound on the other side. They're saying any mechanism you can, after you ask exponentially many queries, I can figure out what's going on.
Linear number of queries, not exponential. Linear number of queries.
No, okay, they have several results.
Yeah.
Let's say the most sophisticated results of the type perhaps you were alluding to say if I'm giving you less than square root of n noise on some constant fraction of the queries and perhaps huge noise on other queries, then I can then I have blatant non-privacy, meaning that I can reconstruct a vector which is close to the original vector even if I knew nothing about the original one. Okay, right, so there are various ways of interpreting the results, that it's impossible, for instance, to have perfect privacy for the data analysis if we want to have privacy for the data set. So something will have to leak, but it's okay, we'll do something like differential privacy for the analyst. You can view it as a negative results about distributing the work of answering queries, well, because either the service must share information about the queries asked, or they can only answer a small number of queries. So you can view this as the bad news. The good news is that we do have some privacy for the analyst. So we, of course, will have to use stateful algorithms. We'll have to settle for less than perfect privacy for the analyst, but something closer to differential privacy for the analyst. And we also assume here that the analyst, this is of course relevant if you have a large number, that they each have an ID, and when they give a query, they say who they are. How you implement it is another issue. Perhaps you use crypto. And what we'll do is we'll construct a stateful mechanism that is differential privacy for their data. We're not going to give that up. And can answer up to an exponential number of counting queries. And the accuracy, in terms of accuracy, will be worse than what we've seen, but not very much worse. And in terms of the analyst privacy is that the view of one analyst is approximately the same distribution, regardless of what other queries are asked by the other analysts. This is what we'll show. So it will be epsilon delta private. So this is the setting, just to answer, I think, a good picture that will answer a myth question. So we have a database. We have lots of different curators, perhaps T curators, and they get the database, and they get perhaps some initial coordination information, like in, for instance, Yael's talk yesterday, where you get some, for instance, they can agree on randomness. There is some initial coordination between them, but after the process starts, They do not talk to each other or to the database. And then the first mechanism gets a query, has to answer it. Second mechanism, of course, perhaps the first mechanism gets other queries, but for simplicity, we'll think of it as if each instance, each server here gets a single query, etc. So this is the setup. And the question is what can we do here? How large can T be?
Without loss, so you're saying you achieve minimal state, just the index number. So essentially you can view it as a curator who just remembers the index
No,
number.
the curator, also common randomness. They do have common randomness.
Yeah, but I'm saying pretending that this is one curator, I mean, it's like a weird setting with multiple curators, but in the normal setting with one curator, you're saying the curator maintains minimal state. I mean, yeah, he knows the
No, the curator can maintain, let's say, state about all the queries that curator received, but of course we're going to simply ask him.
But that's what I'm saying, because you're saying each curator receives only one query and has no idea, he just...
Oh, so he does have an ID. The curator itself has an ID number. So different curators can use slightly different algorithms. That's not the concern.
No, but because each curator answers one query, the only thing he needs to know is what is I, right?
Right.
So
And no, but he also needs to know the database and the common randomness. They do have common randomness. Okay, and maybe other, I don't know what. Okay, so this is what we mean by a stateless query release mechanism. So what we have, there are some known stateless mechanisms. For instance, the independent noise mechanism that we've just seen. There is the famous randomized response mechanism. So what do we do there? The randomized response was a method suggested in the 60s by Stanley Warner. And you could even use it here if I ask you an embarrassing question and I don't know, if you're following some reality show or something like that. Suppose that's considered embarrassing here. And what you'll do, I'll ask you to flip your true answer with a certain probability, but not probability half, and then gather statistical information from it. So in our context, what you do, you take any element in the universe, let's say you put it in your fictitious database with probability half, and the real guys you put in with probability half plus epsilon, so they have a slightly larger probability, and then actually you think of X hat as being the fictitious database as being completely public, and you answer according to X hat. You deduce what happened in the original database so that the expectation is the right one. So for each element, what you've done is you've biased it slightly towards his true answer, biased within it. And each answer is accurate, certainly with error less than with some non-trivial answer, you actually get pretty high probability. And but this is true, of course, only if the universe is small. Okay, if the universe is large, you're losing. If it's larger than n squared, you gain nothing here. But it shows you that for small universes, you can be stateless, and certainly you'll have to have more sophisticated algorithms, adversarial algorithms, than we'll see in a minute. And then you can answer, let's say, just give an answer based, not look at the database, just figure out what would a random database do and answer accordingly. You'll be pretty accurate on random databases. So we'll have to compete with that. And then there is also the issue of a random subsample, which I mentioned. You sample a small fraction of your database, and then you answer everything accordingly. So these guys have taken one for the team. They've given up all their privacy. But this is not the goal in differential privacy. Because this would give you something like 0 polylog over n differential privacy. And we're interested in delta being negligible. Because you don't want people after the fact complaining, why did you do this to me? You're suing, etc. So why is coordination necessary? What is the source of the? And by the way, we didn't know when we started thinking about it. We didn't know where things go because we had all these different mechanisms that were stateless. But the point is that being stateless, you can think of the responses as being some fixed non-adaptive function, well, not exactly function, but a probabilistic function. You have the issue of you have to deal with, let's say, the server number, etc. But all this you can think, but you can really plug it into this probability function. And then what we show is that you can generate correlated responses with a function of an unknown individual xi. And so you will make sure that if it's a function, if the responses are a function, or like a fixed function, it doesn't change. The whole point is that it doesn't change in time. It's a probability function, but it doesn't change. We'll show that you can correlate it with a function, a function of some unknown individual xc. And this function, depending on the setting, would either, depending on how large u is, depending exactly, we'll see, take a simple case. It's going to be either the dictator function or the inner product. If in case it's the inner product function, you can use Goldreich-Levin in order to figure out a guess about the individual. And for the dictator function, it's even simpler. You don't even need that step. Okay, so we'll use some list decoding properties of these things. So what we'll do, we'll think of it as a game. We'll have an adversary A that is going to play the game. The database is uniformly at random. And psi is a uniformly random element of the database. What A knows, what our adversary knows, he knows everything about the database except this element. Okay, and he's going to produce T queries. In our case, they're going to be non-adaptive. But it's bad enough even if they are adaptive. And then he was going to respond he's going to get T responses. They should all be fairly accurate, non-trivially accurate. And then his response is a distribution on the universe. And his payoff is the probability, square root of the probability of the missing element. This is how we define it. And we'll be interested in the expectation of the expected payoff. So of course, if he guesses it, he gets lots. If the output's just a single element and all the rest are zero, he gets lots. And it's the correct one, he gets lots. But this is just a slightly more complex way of defining, doing list decoding. This way of phrasing it, and we get tight answers here. And the expectation is over all the randomness in this game. So this is the total re-identification game. And what you can see quite easily that if you have a too high expectation in this game, if you have an adversary with a high expectation, then you cannot be epsilon differential privacy. Or if you are epsilon differential, if the mechanism is epsilon delta differential privacy, you cannot have a expectation which is larger than something like square root the universe size, something like that, times e to the epsilon plus delta. So here you can see that if the universe size is small, you can have non-trivial things going on. But we'll think of the universe as being larger than n squared. Okay, and what we have is that state is essential, that if you have something like n squared log u queries, you cannot achieve epsilon delta differential privacy. If delta is, let's say, little o of 1 over n. Okay. So we have these requirements. Remember, we need the universe to be larger than n squared, or rather as response works. We need the number of queries to be larger than n squared, or some sort of Laplacian noise works. But if these two conditions hold, and we need delta, of course, to be less than 1 over n, or less than polylog in n, or just a subsample will work. But as long as these things don't happen, then you cannot get epsilon delta differential privacy.
Here you count things as fraction, right? So when you say error at 1 minus delta, it means almost complete, but like 90%. I mean, You
The
measure
delta is the bad event where things. I would want it to be negligible.
no, not delta, gamma. Sorry. This one.
Gamma is the gamma here is the error. Yeah, yeah. This is fraction.
answer
In
is
this case, of
zero
course,
one.
it's a fraction. Anything, or if we're talking about actual numbers, anything that is sublinear is interesting. What this says that if you want sublinear, you're
Money?
Hmm?
Like, I know it violates the definition of differential privacy, but P of gamma 1 over n, it doesn't look so bad.
which one? Delta 1 over?
I mean, P of 1 over n, it means that like the adversary doesn't.
No, this is
completely-
okay. This is just to violate. This says.
Yes.
No, this is just connecting it to this proposition, saying that if you have epsilon delta differential privacy, then you can have at most this payoff. Forget the pay.
Yes.
This is just okay. And this is the interpretation in terms of differential privacy.
Yeah, no, but apart from differential privacy, the violation that.
No, I'm guessing. No, what do you mean? I have a database. I know that someone is a resident of the United States. I have a database on some individuals, and I can reconstruct that person. I know who that person is. Let's say I have a database on 100 people, or not hundreds, slightly. Let's even say 100 people, and suddenly I reconstruct that person with probability even 1 over 100. And I had no idea who he was. He was a random person. And I reconstruct him out of the... Not to mention, let's say I reconstruct his genome. I had no idea who he was. I had some genomic information, and I reconstructed his genome out of it.
You're saying if n is kind of big, then you
No.
didn't.
But the universe is huge.
Okay, okay. We'll also talk... Yeah, the universe can be huge. No, but it's... Okay, this is... This implies that you can... I mean, I can argue it in a formal way. This implies that you cannot have these parameters. But I can also tell you a more concrete story. So this is how the adversary behaves. It looks very much like various proofs we've seen. So the adversary chooses a k, and k is going to be his weight on the database. Oh, now we've switched from 0, 1 to minus 1, 1. So the database is either minus 1 or 1, not 0 or 1. So you choose the weight, you decide how many elements in the data. The adversary knows everything about the element psi, so he knows psi complement. So he chooses k elements in the database that are going to get in his queries, always going to get weight 1, and all the remaining are and all the remaining elements should get a minus 1. Here, this should be a minus 1. And so the part on the database psi is going to be fixed in all his queries. Now what he does, he selects the remaining guys uniformly at random. He does that t times, and then he composes these two parts and gets his t queries. Okay. So the predicate on members of psi complement are always according to Q0, and the elements and those in the complement are always according to Q1 of J. These are his queries. He gets back a bunch of answers, assigns weight CW for each element not in that he doesn't know about, assigns weight CW according to the average answer that he got. This gives you him CW. Now he wants to make CW into a probability distribution, so essentially you remove something from CW, C of W, and you make sure you don't get 0, and you square it. This should be PW, and you should make it into a probability distribution. What could go wrong? You can have too large weight. So if it's larger than 1, you just fail. Your output fail. And we'll have to show that that doesn't happen. So this is his algorithm, very simple algorithm, completely non-adaptive. And you can show that it works because what you're doing is you're correlating yourself with a dictator function psi w, okay? And you're getting something close to it. So you can show that you will get, on the correct value, you'll get what you can show is that on the correct value, on the correct guy, you get for the correct guy, you do get a good correlation. For the incorrect guy, you get no correlation, and you can get from it what you want. Let me skip this. So just you get for the correct guy, the expectation is larger than gamma over 2n. And on the other hand, with pretty large probability, you don't get total weight, which is over 1, so you can make it into a probability distribution. And this gives you the success probability that you're after. So now we know that state is essential. Let's say a few words about stateful, what we can do with IDs. Okay, so we want now is. So remember, each analyst has an ID. I think that it's best to think of it as if there are 2 analysts or 3 analysts or something like that. Okay, and so what do we want? What is our definition now? We have an adversary. The adversary completely controls one of the analysts and knows something about 2 profiles. He has 2 honest query strategies, H0 and H1. And there are strategies of asking queries on other IDs, not his ID. He completely controls one ID. So he just chooses, as an indistinguishability of encryption, he chooses H0 and H1. He chooses his own queries, the queries under his own ID, and then he has to figure out, based on his answers, whether the other queries were H0 or whether they were H1. Okay, he sees, of course, only the responses to his own queries, not to the other queries. And the theorem that we get is that this is we can get epsilon delta. We have a mechanism. We'll see something about it in a minute. It's differentially private for the users. It's epsilon prime, a beta differential, many to one, what we call to the individual. And it's accurate, alpha beta accurate to up to t queries, where now we've gone from square root of n to 4th root of n. Okay, so we are worse than before in terms of accuracy, but it's still sublinear or a little of 1. And as before, we have log dependency on
what is beta? Beta is a probability.
Beta is whatever you want it to be, but it's a probability of success in general. Okay, so here is how the algorithm looks like. We'll have 2 layers. This is the data set. We'll have one layer that will talk directly to the database, and this layer will be in charge of the privacy of the data. Then we'll have a second layer that will talk to the analysts themselves. It will be special to each. For each ID, will have its own copy of the database of the algorithm. So let's say ID1 issues a query. It doesn't talk directly to the database, but it talks to layer 1. That layer issues a query to the data set. Then ID2 issues a query. Then a second query is issued to the data set. And now ID2 issues a query. A third one is issued to the data set. The point is that this algorithm doesn't care at all, this layer doesn't care at all where, in the communication here, you aggregate all queries that you receive. But up here, you give queries depending on the ID, etc. So we have these two layers, and the way we're going to, what algorithms are we going to run in each layer? Well, there was a reason why I showed you the PMW, the private multiplicative weight algorithm. We're going to implement both of them using the PMW algorithm. So we call this one the inner algorithm, and this is the outer algorithm. So the inner algorithm, for the inner algorithm, all we need is some privacy-preserving algorithm. We don't need any special characteristics. We picked PMW because it has good characteristics. For the outer algorithm, we do need special properties of or at least for the proof. You can show that there are algorithms that are very private yet cannot fit for the outer algorithm. And but the PMW algorithm and its analysis just fits what we need for the outer algorithm for PMW-AD. And what we show is that the output distribution of PMW-AD is approximately the same whether it has accessed the real database or whether it accesses it through this noisy version. This is the basis for the analysis for the privacy of the analyst. Okay. So are we done? Hopefully not, because I think that there is lots more to do here. So for instance, I didn't talk at all about collusion among analysts. Okay, in terms of the data, there isn't an issue. It's completely protected whether they collude or not. But what happens? But the argument that I gave, well, I didn't really give, but the argument I alluded to relied on no collusion. And in fact, you can tolerate some sort of collusion. You can also do some more layers than 2 and get something. But each layer, the accuracy deteriorates. So after like log n layers, you'll get not only trivial accuracy. So the obvious question is, can you improve this? Can you allow collusions of large subsets of analysts that and still maintain the privacy of the remaining? This is somewhat reminiscent of broadcast encryption or tracing crater.
Moni, sorry, but I thought you said that it's like all the analysts collude against one guy.
That's fine.
It's even better. Right?
No, sorry. One guy against all the analysts. If you okay, one guy against all the analysts. If you know the subset, obviously it's very easy. But the real issue is if you have lots of different possibilities and you just don't know whom to protect and whom not. And I'm not talking about adaptive security here at all. The error complexity. So we had worse error than the plain one. Obvious question: is this necessary or not? Do we have to suffer this deterioration due to the 2-level mechanism that we have? Maybe there is a way to bypass it, or can you derive some lower bound? The other thing is, I mean, this is related to the collusion one. I mean, ideally, it's not the curator, the mechanism's business. What my ID is. The ideal algorithm would just answer queries. That's it. Wouldn't worry at all where they come from, and hope and things should somehow work out. Is this possible, or is there an impossibility result here? And then the obvious thing is, okay, now we're in a distributed manner. What is the minimal amount of communication that we need between the different curators in order to be able to answer a large number of queries? And then I talked only about counting queries. Probably things work out for low sensitivity queries, but you can think of general queries and ask whether you can repeat, whether there's some sort of compiler that takes any sort of mechanism that is good against many queries and translate it into a data analyst version. Thank you.
you have any questions or comments? You've been
So in your kind of model, I just want to understand, you kind of assume that the way you achieve privacy again is this analyst, as each analyst has to declare who he is, and the database really, the sanitizer uses exactly this information to make sure to protect again is this guy, right?
Right.
This is kind of you're saying the weakness, because in reality, if you don't know if like the query is anonymous,
If the queries are anonymous in this mechanism, remember this picture, right? You had to channel the query to the correct place.
is it impossible to have impossibility result anonymous?
I'm saying this is one of the open questions.
Places are, so I'm just slow.
This,
I'm just slow.
slow children ahead.
This is the end of the week. You're allowed to be slow at this point. Okay. So any other questions? Oh, yeah.
So, if I understood correctly, you were saying that in effect, the view is that n squared queries on a database with n records is considered too small. But that seems, the view seems to be that the database is a static thing during those n squared queries, whereas in a typical scenario, records are being added, and I mean, n squared seems like a lot of queries on a large database. So.
Right. Okay. So
And in between those, maybe the database itself is getting upgraded and maybe updated, and maybe then the result doesn't apply.
okay. So if you have several issues which are all excellent. So first, we also get, you can scale. I mean, you get things deteriorate between n and n squared. Things deteriorate. We get something from n, but on the other hand, we saw that you can get that even the Laplace mechanism buys you something for up to n queries or n to the 1.5 queries. So we cannot rule out such things. Now about the database being updated, that's good. So we have there is work on continual output databases where exactly these things happen. There isn't. The things there are much less sophisticated than the queries we have here. But in principle, you could ask all the questions on a continually changing database, with a continual output, etc. But the answer is that we know things like counting and Google Trends. You could do this way, but we don't have. We don't know how to replicate, let's say, the PMW algorithm in this setting.
Thanks, speaker again. Thank you.